All right, now we're going on to part 2 of section 9.1. And we're going to look at inverses and one-to-one functions. Let's look at the following two functions as a relations. And another word we may have used is correspondence. Relations is equivalent to correspondence. So here we have countries and their capitals. These are the list of countries. That is your set of inputs. This would be your X items. Then the range, which would be Y items, which are your outputs. And notice there's a one-to-one relationship or correspondence. So this is a function. Now, as we look at phone keys in various places or items or telephones, the set of inputs are A, B, C through F. And notice there's just one arrow coming out of each one of these. So in this correspondence, these are your X's. Again, that's your domain. And these numbers 2 and 3 are the range, which are your outputs. Now notice this is also a function because the X element is only used once. Now if we reverse the arrows, that is in a sense making our domains on this side and range on this side. Again, we're still thinking of domain as being X and domain as being X, and then range as being Y. Here, again, domain items are only used once. So yes, this is a function. But when we look at this now, we see many arrows coming from the 2 and the 3. So here it is not a function. So in summary, recall that for each input, a function provides exactly one output. That is, the X is only used once. However, it is possible for different inputs to correspond to the same output. Only when this possibility is excluded will the inverse be a function. So here the inverse is a function, but here the inverse is not a function. And taking it just a little bit further, when we talked of the capitals, each input has its own output, so it is what is called a one-to-one function. In the phone keys, that is not a one-to-one function because A and B were both paired, and originally these were X values were paired with the 2, so that wasn't one-to-one. It was still a function, but not one-to-one. Okay, let's look at one-to-one function. A function f is one-to-one if different inputs have different outputs. That is, if for A and B in the domain, which are your X values, of f, a does not equal b. So we have this function symbolism. Then this is 1 to 1. If a function is 1 to 1, then its inverse correspondence or relations is also a function. And you can use the chart we just went over. How can we tell graphically whether a function is 1 to 1? Well, let's look at this graph here. For example, 5. Okay, as we look at this, here we see sort of a curve. Looks like maybe half of a parabola. Now, is this line, as we see it from the old days, a function? Well, you all remember, or should remember, what is called the vertical line test. That is, when we take a horizontal line, a vertical line, and move it across the face of our graph. Does this vertical line intersect this graph in more than one place? And the answer is no. If so, then we say it is past the vertical line test, and this is a function. Now, they're also saying that how about whether its inverse would be a function? Well, we have another test, and this test is called the horizontal line test. So as we take this line, which is horizontal, and move this over the face of our graph, does it intersect this graph in more than one place? And the answer is no. So this graph passes the horizontal line graph. If it passes the horizontal line graph, then its inverse is a function. And it says the graph of every function must pass the vertical line test. In order for a function to have an inverse that is a function, it must pass the horizontal line test as well. So let's take a look at the horizontal line test. So as we look at the horizontal line test, it says it is impossible to draw a horizontal line that intersects a function's graph more than once. Then the function is 1 to 1. For every 1 to 1 function, an inverse function exists. So as we look at example 6, determine whether this function, which is one of our old friends, a typical parabola, is 1 to 1 and thus has an inverse that is a function. Well, when we graph this, remember its origin is going to be right there at the origin. This is the minimum of the graph. Its x-asymptote is the y-axis. And if we apply, and this little light blue line here is the horizontal line test. Is this intersecting the parabola horizontally in more than one place? Yes, it's intersecting in two. In fact, all over the place it's intersecting in two places. So horizontally, this does not pass the horizontal line test. So it's the inverse of this would not be a function. and here is the work to support it. All right, let's go on. And we want to state the summation of this. Thus, the function is not one-to-one, and no inverse function exists. Now we can go to the next page. Okay, finding formulas for inverses. When the inverse of f is also a function, it is denoted as f inverse. Now, you might recall that we had used negative exponents in other lessons. This is not a negative exponent, even though it looks like it. This is a function symbol and is read f inverse. So here again, the -1 in f inverse is not an exponent. Okay? So let's go on. Now, this is rather detailed, so you can read it along with me. Suppose a function is described by a formula. If its inverse is a function, how do we find the formula for the inverse? For any equation in two variables, that's if we have like an x and a y, if we interchange the variables, that is, reverse that, so it now becomes y comma x, we form an equation of the inverse correspondence. If it is a function, we proceed as follows to find the formula for f inverse. Let's take a look at this little recipe here. First, make sure that f is one-to-one. So again, you do not want to, as you look at it, it's one line to each of these things and not one line to two things. This gives you the one-to-one relationship. Interchange the x and y. This gives you the inverse function. Then you solve for the letter y. Replace the y with its inverse function x. This is inverse function notation. Okay, let's take a look at this student note here too. This is significant. It says, since we interchange x and y to find an equation for the inverse, the domain of the function is the range of the inverse. And when you reverse it, the range of the function is the domain of the inverse. And we'll be showing some examples of this in a little while. Now, we're going to start off real easy. And first of all, determine whether each function is a one-to-one. And if it is, find the formula for f inverse. Now, as we look at this graph, an old friend, y equals x plus 2. So your y-intercept is 2. Your slope is 1, so over 1, up 1. And then there's your line. Now, is this a function? Well, it passes the vertical line test. And is it a one-to-one? And the answer is yes. The x is only used once. The vertical line test tells you it is a function. Now, does it pass the horizontal line test? And the answer is yes, it passes that as well. So, it is an inverse function as well. Now, what is the new equation of F inverse? All right, it's really easy to follow. So y equals x plus 2. Now they say what we do is we reverse the letters. This x goes over here, and the y then goes over here. Now the next step is solve for y. Well, y is going to stay there, and then my 2 goes over to the other side, and we get x minus 2. This is the inverse function of this, and it's written like so. Okay, it said in this case the function adds 2 to all inputs. Thus, to undo f, the function must subtract 2 from its inputs. So here we added 2. Now we have to subtract 2. All right, let's do letter B. Now in letter B, here's our basic function, and it's linear. In fact, I made a graph of it. -3 is our y-intercept. Our slope is 2 over 1, so we went over 1 up 2. There's our line. It passes the vertical line test, so it is a function. It also passes the horizontal line test, so is a 1-to-1. Now let's use this formula. Y equals 2x minus 3. We're now going to replace and reverse the x with the y. And now we're going to solve for y. We transpose the 3, becomes a positive 3, and then we divide everything by 2, and we get y equals this. We now replace the y, and it becomes the inverse function, which is, this remember stands for a y, x plus 3 divided by 2. And I'm very pleased they put the horizontal division bar. In this case, the function doubles all inputs, then subtracts 3 up here. Double the input, subtract 3. So to undo it, we must, as they say, add 3 to each input and then divide by 2. Now in this next part, we're going to graph functions and their inverses. How do the graphs of a function and its inverse compare? Well, they want us to graph this one and then graph this one on the same set of axes and then compare. So let's move it up a little bit because they have it all done right here. Now here in class, of course, we will illustrate this. I always like to do this with a piece of paper, but let's see how to set it up. Okay, a lot of stuff going on here. So this was our original line in blue, which they have. Actually, that one's in red over there. And our original line was this one, -3 over 1 up 2. And now the inverse of it, and I wrote it as y equals x over 2 and 3 over 2. And then I made this into 1/2 x plus 3/2. To graph it, I went up to my y-intercept, which was 1.5, which is right there. And then I went over 2 and up 1, and that gave me this line. Now, an interesting thing, there is a line of symmetry going up, which is y equals x, that if we were able to fold this paper along this dotted line here, and they're trying to illustrate that, this blue line would actually be right on top of this red line. Okay? So this is called a reflection of our blue line is the red line. And that's the inverse of what we're illustrating here. And how did we do it? Well, we did the first line. And our line of symmetry is y equals x, which is this black dotted line, which they're showing you there. And then if you fold it along that black dotted line, and if this were like wet ink, it would actually make this line up here. So this is a reflection. Let's continue. When x and y are interchanged to find the formula for the inverse, we are in effect reflecting or flipping the graph of this across the y equals x, which is that line of symmetry there. So, for example, when the coordinates of the xy or the y-intercept of the graph is this, they are reversed to get the x-intercept of our inverse function. Okay, lots of stuff going on here. Let's try another example here. Visualizing inverses. The graph of the inverse is a reflection of the graph of x across the y equals x line. All right, so let's determine a couple of things as we consider this function. Now this is to the third degree, and I'm wondering how many of these we will be giving you, because they're so much easier to graph if you have a graphing calculator. But let's see what we can do with them. Anyway, this is a typical of, let me just do a little quick review here. If we had f of x equals x cubed, we would have this graph, and then since our y-intercept here is 2, that's where our y-intercept is, at 2. But if it were just this, without the 2, this would shift down, and it would cross like so. Okay? So this whole thing would shift down. That's all that's happening. Well, determine whether the function is 1 to 1. Well, is this a function? It is a function for x, and it is a function for the inverse because it passes the horizontal line test. Now, we're going to solve it, and let's raise it up a little bit here. We replace our y with the x, which is what they've done. We then solve for y by taking the 2 over to the other side. It becomes a negative 2. We then take the cube root of both sides and we get this. So this is the inverse. Now if we are to graph that, it's a little bit tedious. I believe they have it here in our book. Now there they have it. Notice it's shift down, and if we draw our y equals x line of symmetry, if we were to fold these, we can reflect the graph across the line as we did in example 8. We can also graph this by plotting points. Note that 210 is on the graph of G, which is our first one. And then if we reverse the points, 10, 2, that's on the graph of the inverse. And here they are shown together. So you'd have to study this, and I'm not sure. I think what I'm going to ask is that you are able to recognize that this type of curve is a cubic function. And then when it swings down this way, and you get this reflection along the y equals x axis of symmetry, you get that reflection. This is what it would look like. And of course, you're going to need to be able to do the algebra to show the inverse. Now they say a picture is worth 1,000 words. This one is a really good example of it. Here we're looking at inverse functions and composition. Let's consider inverse of functions in terms of function machines. Suppose that a one-to-one function f is programmed into the machine. Let's say this one. So you're putting in your x's and you're getting your function outputs. If the machine runs in reverse, it performs the inverse function. Again, this is not a negative exponent. It's the symbol for inverse function. Input then enters this way, and the output then is this. An excellent example of what's going on. So let's consider what they're showing us here. Consider this and its inverse, which is this, from the example we did in number 9. For the input of 3. So this becomes 3 times 3 is 27 plus 2. This gives you a 29. They have it worked out here. Now, for the inverse, where our results is 29, we then put a 29 where the x is. 29 minus 2 is 27, and then the cube root of it is 3. So here we input 3, our output is 29. Here we input in its inverse form 29, and our output is 3. And again, they're showing a little nice diagram here. Very good. So in general, if f is 1-to-1, then it's inverse function takes the output, whatever you get for that, back to x. Similarly, the output, which is the inverse function, whatever you get for that, brings you back to your original. That's what they're saying. And now let's put it into a formula. Okay, let's take a shot at this now. We want to see if, in example 10, let this function show that its f inverse function is in fact true. And we're going to do this through our composite or f inverse circle f of x and f circle f inverse of x and checks to see that each of it comes out as an x. So we'll follow this carefully and slowly, because to write all this down would be rather tedious. Keeping in mind this is our standard, and this is basically y equals this and y equals this. This is the inverse. So we're doing our first one where our x is right here, and for that one it's this up here. So we put that in this formula where the x is. We're going to put it right there. Now when we do the math, we can take away the parentheses. This becomes 2x plus 1 minus 1. These just cancel out and we get 2x over 2. The 2's cancel out and we're left with x. So we've proved that this is x. Now we're going to reverse it as we do in a composite, switch our letters around, and we're going to say the function circle of f inverse of x is this. And again, our x here for inverse is this over here, up there, and there it is. Now we're now going to put this in this formula. Where that x is, that's where we're going to put this. So notice here, the 2's cancel out, and we get x minus 1 plus 1. This cancels out, and we're left with x. So it does prove it, that x is x for each of these functions. That is, we started with something, went around, and in its reverse and in its forward direction, so to speak, we get the same answer. Now, again, we're not going to feature the graphing calculator, but in a way, boy, that would be a good tool to have. And they do show you lots of things. And then, of course, they get on here to our examples. Let's just look at them down here. And there we will be in your practice working on these. And of course, this is how you will gain mastery. And I've worked it so I've taken out the real difficult ones. It should be something, if you understand the process and study it, should do well. Okay, that'll wrap up section 9.1